All right, let's look at problem number 3. It's a magnetic flux problem. It says a square loop of wire of side 0.2 meters has a total resistance of 0.6 ohms. The loop is positioned in a uniform magnetic field. The X's indicate that it's going into the page, and that magnetic field has a field strength of 0.030 teslas. The field is directed into the page perpendicular to the plane of the loop. A says calculate the magnetic flux through the loop. Well, A is pretty simple. A says we got to remember that the equation for the magnetic flux is B dot A, which is, because they're perpendicular, I don't need to worry about the cosine of theta and the dot product, so I just have the magnetic field strength, 0.030 teslas, times the area of the loop, which is, since it's a square, it's easy, 0.20 meters squared, and that math is going to give me 1.2 times 10 to the negative third Tesla meters squared. That is the strength of the magnetic flux. Okay, now the electric field increases from 0.2 teslas, increases to 0.2 teslas in 0.5 seconds, so half a second. Calculate the induced EMF in a loop during this period. Well, again, let's go ahead and say, all right, my induced EMF is my change in flux over my change in time, which is my change in BA over change in time. Pretty simple again. My change in flux goes from, it says it's going to 0.2 teslas, so my final is 0.2 teslas. My initial was 0.03 teslas. My area is, again, 0.20 meters squared, and my change in time says it happens over a period of 0.5 seconds. That gives me an induced electromotive force, an induced voltage of 0.014 volts. That is my induced electromotive force. Now, C says to calculate the magnitude of the current in the loop during this period. So if I'm looking for the magnitude of the current in the loop, I know that, I know that my induced electromotive force was 0.014 volts, and Ohm's law tells me that current is your voltage divided by your resistance, so it's 0.014 volts. The resistance was 0.6 ohms, so I'm left with a very easy calculation again of 0.023 amps of current. That is my induced current during this period. Now we get to part 2 of this question that says, what's the direction of current in the loop? Well, I know that the field is increasing into the page in 0.5 seconds. Lenz's law says that if there's an increase into the page, the induced magnetic field will oppose this increase. So the induced current on the inside of that loop should be coming out of the page. So if I do my right-hand rule, coming out of the page, the current's going to be going up on the right, to the left on the top, down on the left. So I know that it's going to be going counterclockwise. When it says justify your answer, this is where during this justification I need to say the magnetic field is increasing into the page. Current will be induced to oppose that change due to Lenz's law. By the right-hand rule, to create a field out of the page, the current must be counterclockwise. Now, for part D, it says describe a method by which you can induce a current in the loop if the magnetic field remained constant. We know that current will be induced by an electromotive force if there's a change in flux over the change in time, which means either the magnetic field or the area has to change. Which means that This one was an example. Part C asks us an example of if the magnetic field strength changes. Well, Part D says, how could you induce a current if the magnetic field remains constant? So you'd have to change the area. You could do that by, you could describe either a rotating loop, you could describe a change in area of the loop, or you could say we're going to move the loop out of the field. Those are the three ways that you could change the current, change the strength of the magnetic field by changing the area. And that is the answer for problem 3. And that is the answer for problem 3.